In the last days, an interstellar visitor turned an electric blue and blinked in ways no ordinary comet usually does, glinting, brightening, and appearing to kick itself along its orbit. In this video, I'll walk you through exactly what was seen, what real science can explain, and which possibilities are still left on the table. Hello. Today we unpacking a puzzling set of observations that have captured attention across the astronomy community. This is not a jump to conclusions episode. Instead, we'll carefully look at the facts, separate what we actually know from what's still speculative, and explain the physics behind each plausible explanation. By the end, you'll understand why this object is so interesting and what to watch for next. First, the facts, plain and simple. Observers recorded three things that stand out together: a sudden and significant brightening, a striking blue hue in its glow, and small departures from the expected orbital motion. Any one of these phenomena can occur with comets. All three together are what make this case unusual. The brightening happened as the object approached close to the sun. The color shifted toward a vivid blue that is not the typical greenish or dusty tint most comets show. And positional measurements indicated slight acceleration components that don't match the simple gravity-only prediction. Now let's unpack each of these pieces and what they tell us. Why color matters. Color is not cosmetic in astronomy, it's diagnostic. The colors we see in cometary and tails arise from specific molecules and the way sunlight interacts with gas and dust. A familiar greenish glow in many comets is tied to certain carbon molecules. A pronounced blue, however, suggests either a dominance of differently ionized species, very fine charged dust, or scattering effects where small particles preferentially reflect shorter wavelengths. In short, the blue points to something distinctive about the material being released and how it is interacting with the solar radiation environment. Why the sudden brightening matters. Comets brighten when sunlight heats volatile ices and causes them to sublimate, releasing gas and dust. Rapid brightening can happen when previously insulated volatile pockets are suddenly exposed, for example, if an overlying crust fractures or if the object experiences fragmentation. Alternatively, exotic or volatile rich ices that sublimate vigorously at certain distances can produce dramatic outbursts. Brightening is a sign that material is being liberated rapidly into space, and that, in turn, ties back to the color question because the newly released material determines the observed spectrum. Why unusual motion matters. When astronomers describe non-gravitational acceleration, they mean the object's motion includes small pushes that gravity alone cannot account for. In comets, the most common source of those pushes is outgassing, jets of gas and entrained dust blasting off the surface in preferred directions, acting like tiny thrusters. Other causes include radiation pressure on asymmetric shapes, fragmentation altering the center of mass, or measurement uncertainties. Distinguishing between those possibilities requires careful, repeated position measurements and modeling. So, what are the leading plausible explanations? Let's consider them in order from most likely to least likely, given the current picture. Natural cometary behavior with unusual composition or structure. This is the simplest, scientifically conservative explanation. If the object's surface had a fragile crust, cosmic irradiation or thermal stresses near the sun could fracture it and expose volatile-rich layers. Those volatiles could sublimate aggressively, producing fast brightening and a plume enriched in ionized species that emit blue light. Asymmetric jets from this outgassing can produce small accelerations that mimic thrust-like behavior. In this scenario, there is nothing extraterrestrial in the sense of technology. Instead, you have a rare combination of composition and structural fragility that produces dramatic effects when heated. A disrupted or fragmenting body with exposure of fresh ices. If the object is breaking into pieces, internal pockets of volatile ices may suddenly vaporize. Fragmentation can temporarily increase surface area and create complex jet geometries. The particle size distribution of the ejected material could favor very fine dust that scatters blue light. Fragmentation can also lead to apparent oddities in motion because different fragments and ejected material change the effective mass distribution and the center of light, which affects astrometric tracking. This hypothesis overlaps with the first but emphasizes mechanical breakdown rather than a fragile crust alone. Uncommon ices or chemical processes under intense solar radiation. Interstellar objects have experienced long exposure to cosmic rays and interstellar chemistry that may produce exotic layers. Some molecules or complex organics, when irradiated and then heated, produce emission lines or particle products uncommon in typical solar system comets. Additionally, charged particles near the Sun can alter dust charging behavior and change scattering properties, amplifying blue emission. This is a chemical physics explanation that requires spectroscopic confirmation to pin down the actual molecules involved, geometric and observational factors. Sometimes a combination of geometry, viewing angle, phase angle with respect to the Sun, and line-of-sight dust configuration can exaggerate certain colors or apparent brightness changes. Measurement cadence or instrument sensitivities also matter. An instrument tuned for certain wavelengths might emphasize blue features. Before leaping to exotic explanations, scientists always recheck calibrations, instrument responses, and observation geometry. Artificial propulsion or engineered origin, highly speculative and least likely. This idea attracts attention because it is dramatic. Could a non-natural cause explain the apparent tiny kicks or unusual behavior? Science demands evidence commensurate with extraordinary claims, repeated, sustained, maneuver-like accelerations, clear engineering signatures, or emissions consistent with controlled activity would be needed to support such a claim. So far, the data as a whole do not meet that threshold. The observed accelerations are stone-cold explainable through natural processes like jets and fragmentation, and the blue glow has plausible natural chemistry-based causes. That said, considering all hypotheses is part of how science works, but extraordinary conclusions require extraordinary confirmation. What would we need next to narrow these down? 3 types of follow-up observations are most valuable. High-quality spectroscopy. Spectral lines identify specific molecules and ionization states. A detailed spectrum will reveal which atoms or molecules dominate the glow and whether the emission pattern matches ion tails, dust scattering, or rare chemical species. Precise astrometric tracking, repeated, accurate position measurements over time will determine whether the non-gravitational components persist and whether they match jet models. If accelerations are transient and correlate with bursts of brightness, that strongly points to outgassing jets, imaging and temporal monitoring. Watching the object evolve, whether it fragments, how its coma develops, and how brightness changes will test fragmentation and transient exposure scenarios. Imaging from a variety of instruments and wavelengths helps build a complete picture. So, where does that leave us right now? The most parsimonious interpretation is that this is a natural object, an interstellar body displaying exotic but physically consistent cometary behavior. Unusual composition or structure combined with dynamic activity near the Sun producing blue emission and jet-like outgassing. The alternative scenarios are worth keeping in mind, but they require stronger, repeatable evidence to be favored. A few practical notes if you're following this story. Avoid one-off sensational interpretations. Look for consistent, multi-instrument measurements. And value spectroscopy and trajectory analyses above headlines. Scientists are cautious for good reason. That caution does not mean the object isn't interesting. It is exactly the opposite. The more puzzling the observations, the more careful and valuable the science becomes. These events push our understanding and force the development of better models for rare visitors. Finally, what should you watch for in the coming days and weeks? Look for clear, published spectra that list emission lines, precise orbit updates showing whether non-gravitational acceleration persists, and imaging that shows fragmentation or evolving coma structure. Those three data streams will move the discussion from mystery toward a robust explanation. If you enjoyed this breakdown and want continuous updates, consider subscribing for concise, evidence-driven updates when new observations come in. And if you have a theory or a paper you think is relevant, share it in the comments. Civil, sourced discussion helps everyone learn faster. Thanks for watching, and until next time, keep curiosity honest and skepticism constructive.